Assalamu alaikum. Welcome to this online lecture series on data mining. In this lecture, I'm going to discuss different applications of association rule mining and pattern discovery. We'll first discuss the another interesting task of association rule mining, which is about spatial frequent pattern mining or spatial patterns or spatial frequent patterns. Then we will move towards the applications of pattern mining in this area of spatial associations and mining spatial colocation patterns. In last lecture, we had discussed the basic concepts of sequential pattern mining, as well as we had discussed some algorithms used for mining sequential patterns. Like one of them was SPAT, which is vertical format based sequential pattern mining, and the other one is prefix span, which is a pattern growth based sequential pattern mining approach. In this lecture, I will first discuss some concepts of spatial frequent patterns, and then we will move towards how we can mine spatial associations or spatial frequent patterns. So spatial associations or spatial frequent patterns share some commonalities with the general associations or frequent patterns. For example, these association rules are also in the form of A implies B with some certain confidence and support values. So in this context, A and B could be sets of spatial or non-spatial predicates. The spatial predicates may include the predicates actually are the the premises and conclusions of the association rules. So the spatial predicates may indicate some topological relationships or relations like intersects, overlaps, or disjoint and similar kind of things. Or spatial predicates may also be indicated by some spatial orientation like left of, west of, under or above and similar things. Similarly, we can represent spatial predicates with some kind of distance information like close to something or within a distance and so on. So if we summarize this, so spatial means some kind of location or with respect to space. So these all three predicates represent some, almost the similar kind of information. Like topological means with respect to the physical location or physical existence of things, like one thing intersects with some other thing, or something may overlaps with some other thing, or if we want to disjoint something from another thing. So this is a topological relations. Similarly, we have some spatial orientation, means orientation with respect to the space, with respect to location. So like if x is on the left of y, or x is the orientation of x and y is x is on the west of y. Similarly, if we want to represent the orientation of x and y, that x is under y. So this is again the spatial or location information. So similarly, the third one is distance information. Like if we want to show the distance of two objects or two locations, so again this is the property of the space, or with respect to space or location, or in short spatial association. So like we can say close to or within distance, similarly the other things. Similarly, we have the same kind of measures or evaluation criteria as we have the in our general association rules, like the same measures we have sport and confidence of the rule. So these two parameters as we have used in order to evaluate the patterns of simple or general association rules, we use these those same parameters or same measures in order to evaluate the spatial frequent patterns. Then the spatial association rules can be we can find it could be like, if X is a large town and X intersects with some highway, then X is likely to be adjacent to water or with water related area like some lakes or rivers or ocean. So so that with some certain sport and confidence. You can see this is the similar type of or similar form of the association rules that we have used in general association rules. So in spatial data mining, we quite often would like to explore spatial autocorrelation. That means spatial data tends to be highly self-correlated, like nearby things are more related than the remote things. For example, when we study neighborhood, or when we study temperature, so we can see that nearby things are more related than the remote things. Okay, so in spatial association mining, there is an interesting heuristic called progressive refinement. The general philosophy with this progressive refinement, like for a spatial relationship, there are some rough relationships like close to. These are the rough representations or generalization of some more refined ones like nearby, touch or intersect or contain. So they are somewhat all close to. Like if we say this is close to, which is the ये एक generalized और rough form है, जैसे like अगर हम बात करें नियर बाय की, like close to, हम close to उसका मतलब हो सकता है कि वो एक चीज़ दूसरी चीज़ के नियर है, या एक चीज़ दूसरी चीज़ को टच कर रही है, या एक चीज़ दूसरी चीज़ के साथ इंटरसेक्ट कर रही है, सो वो भी क्लोज टू होगी. लेकिन अगर हम साथ ही कंटेन की बात करें तो वो भी अगर एक चीज़ दूसरी चीज़ को कंटेन कर रही है, तो उसका मतलब भी यही है कि दो चीज़ें आपस में एक दूसरे के क्लोज हैं. So these are the more refined representations, but on the other hand, this close to is the generalized or rough form of representation of these more refined terms. So the progressive refinement says that first we search for rough relationships and then we can go for more refined ones. मतलब ये है कि हम स्पेशल एसोसिएशन रूल माइनिंग में पहले हम लोग रफ रिलेशनशिप्स को फाइंड करते हैं. अगर रफ जो रिलेशनशिप्स हम फाइंड कर रहे हैं अगर वो फ्रीक्वेंट हैं, देन हम लोग मूव करते हैं मोर रिफाइंड रिलेशनशिप्स को फाइंड करने के लिए. लाइक अगर हमारे रफ रिलेशंस ही फ्रीक्वेंट नहीं आ रहे, सो हम नेक्स्ट रिफाइंड पैटर्न्स को या फ्रीक्वेंट पैटर्न्स को माइन करने की तरफ नहीं जाएंगे. ऑब्वियसली जब रफ रिलेशंस फ्रीक्वेंट नहीं है तो देन उसकी रिफाइंड फॉर्म्स भी कभी भी फ्रीक्वेंट नहीं हो सकती. So just to give you an example, like here you can see near a highway intersection you may be able to find some shopping centers and some gas stations and some other similar kind of buildings or points, but how close to, whether they are very nearby or they almost touch the highway intersection. So यहाँ पे हमने अगेन वही बात की कि आइदर दीज जो पॉइंट्स हैं हमारे पास, शॉपिंग सेंटर्स हैं या गैस स्टेशंस हैं या दूसरे कोई पॉइंट्स हैं, वो हमने ये तो कह दिया कि ये क्लोज टू हाईवे इंटरसेक्शन है, बट हमें ये एक रफ रिप्रेजेंटेशन है, लेकिन हमें ये नहीं पता कि वो नियर हैं उसके हाईवे इंटरसेक्शन के, या वो उसको टच कर रहे हैं या वो उसको इंटरसेक्ट कर रहे हैं. सो ये इंफॉर्मेशन, ये एक रिफाइंड फॉर्म या रिफाइंड इंफॉर्मेशन है हमारे पास. लेकिन अगर हम सिर्फ ये कहें कि जो गैस स्टेशन है या कोई शॉपिंग सेंटर है वो क्लोज टू एंड हाईवे है, सो इसका मतलब एक रफ फॉर्म है हमारे पास, हमें क्लियर पिक्चर नहीं है कि वो कितने क्लोज हैं उस हाईवे इंटरसेक्शन के. सो इन दैट सेंस those are detailed relationships like nearby, touch, intersect or the similar kind of things. However, if we first find those close to, they are frequent together. If rough ones are frequent together, then if we want to find that it more refine, how close to are they really to the intersection. So we can say if the close to is a frequent pattern, then we are going to study the more refined ones. So to that extent, this is the philosophy of progressive refinement. That means we first search for rough relationships and then refine to study more refined relationships. The general philosophy is, if the rough relationships is not frequent, so there is no need to study the very refined ones, because they are not frequent as well. Because if their rough relationships or rough representations are not frequent, then their refined forms cannot be frequent as well. So to the extent we can do two-step mining of spatial association. So the first step is we use reasonably cheap or low cost algorithms like minimum bounding rectangle or R-tree for some rough pattern mining. That means we first compute the rough spatial frequent patterns, then we know if the rough one is frequent, then we are going to get into more refinement process. That means we may study more detailed algorithms using more refined data structure, so that this principle can save a lot of mining cost. Because we first use rough ones, we get a big filter like this. The rough representations work. Where is the cursor? Like the rough ones act as a filter because it filters a lot of unnecessary pairs because they are not frequent already, so we do not have to refine them. So we do not have to use refined methods to study more refined patterns. So now we will discuss the applications of spatial association. Like we'll learn how to mine spatial colocation patterns. So what is spatial colocation pattern? Usually a group of spatial features or events can be frequently correlated or co-located in the same region. For example, West Nile virus may often occur in the regions with a poor mosquito control and the presence of birds. Like West Nile virus is a type of virus which may occur in the regions where a poor mosquito control and the presence of birds. So these two are the the reasons for the creation of the West Nile virus. So if we can find such patterns, we may have better way to control the spread of this virus. So let's look at this example on the right. So we have A, B, C and D as 4 type of objects. You can think A could be a West Nile virus, which is the spreading region. Similarly, B could be some mosquito region, or C could be in these some cities, and D could be the presence of birds or something. Okay, then we use the edges, means they are co-located. Like if we connect this A with B, A is the red square and B is the plus sign. So the edge between these two means that the A and B are co-located regions. Similarly, for example, 3, 6 and 17 are co-located. We use edge or link them together, and 4, 7, 10 and 16, like here, are co-located together. We use the edges linking them together. Okay, like 2, 9 could be co-located like this. 2, 9 could be co-located, but on the other hand, a 2, 14, 8, 11 and 15, these are also co-located regions. Then we may be able to find row set. Row set means if we want to find A, B, C, D, okay, row set means how many objects are co-located together as A, B, C, D, 4 types. So we may be able to find 4, 7, 10 and 16 are co-located like here. So this is a row set. And similarly 2, 11, 14 and 15, 2, 11, 14 and 15 are co-located. Or similarly 8, 11, 14 and 15 are so co-located. That means A, B, C, D, from this A, B, C, D we may find two, actually these 3, one this 4, 7, 10, 16, 2, 11, 14, 15 and 8, 11, 14, 15. These are A, B, C, D, like 4, 7, 10, 16. This is A, this is B, this is C and this one is D. So these A, B, C, D are co-located. So this is a row set. Similarly, if we talk about this A, this one is this is A 14 and this one is 2 is B, and then this is C, and then this one is D. So 2, 14, 11 and 15 is another row set. Similarly 14, 8, 11 and 15 is another row set. So there are 3 row sets of A, B, C, D. Similarly, if we want to find the row set A, B, so now we have to check for A and B. We have to check for the red circle and the positive sign. So we have 5 and 13 as a one row set of AB. Similarly, we have 17 and 10, sorry 7 and 10, which is this. So this is another row set of AB because they are collocated. Similarly, we have 2, 14 like this. This is a row set of AB because they are collocated. Similarly, we have 8 and 14. This is again the row set of AB. So here we have 4 row sets of AB and 3 row sets for AB, CD. Then we may get a collocation rule like this, like A imply B. Like if pattern A is collocated, then whether pattern B is also collocated. So we may find this conditional probability of the collocation pattern. That means if we want to find AB imply CD, that means if AB are collocated or if AB are linked together, then likely CD will be collocated with certain probability. That means we need to calculate, what we need to calculate is ABCD is a row set. Like ABCD is a row set, you probably can see there are 3 such cases, like here as we have had calculated earlier, that here we have 3 such cases in which A, B, C and D are collocated and they occur together. But there are 4 such cases, like in which A and B are collocated or occur together, like when we had calculated the row set of AB, we had calculated that there are 4 such cases in which A and B are linked together. So the condition, if you find AB, then you find CD are collocated, then the condition actually 3/4, which gives us the 75%. That means the conditional probability for this rule is 75%. Okay, I hope you understand. I'm again explain it this example, like अगर हम लोग ये स्पेशल एसोसिएशन या स्पेशल कोलोकेशन पैटर्न फाइंड करना चाह रहे हैं कि अगर ए बी पैटर्न्स जो हैं वो लिंक्ड हैं या कोलोकेटेड हैं, सो देन कितनी प्रोबेबिलिटी है कि सी डी पैटर्न्स जो हैं वो भी कोलोकेटेड होंगे. ओके, सो दिस फॉर दिस लाइक जैसा कि हमने यहाँ पे रो सेट्स कैलकुलेट किए, हमने ए बी सी डी के लिए कैलकुलेट किया. सो वहाँ पे हम लोगों ने फाइंड किया कि ए बी सी डी रो सेट मीन्स क्या है कि ए बी सी डी टुगेदर कितनी बार अकर हुए हैं. तो हमने फाइंड किया कि 1 टाइम्स हियर, सेकेंड टाइम्स हियर एंड थर्ड टाइम्स हियर. सो हमारे पास 3 सच केसेस थे कि ए बी सी डी कोलोकेटेड पैटर्न्स हमारे पास हैं. सिमिलरली फिर हमने फाइंड किया कि रो सेट ऑफ ए बी, हमारे पास 4 सच केसेस थे जहाँ पे ए बी पैटर्न्स लिंक्ड थे या कोलोकेटेड पैटर्न्स थे. सो यहाँ से अगर हम लोग इस रूल की प्रोबेबिलिटी फाइंड करना चाह रहे हैं, सो हमारे पास ए बी सी डी की प्रोबेबिलिटी क्या या अक्रंस या फ्रिक्वेंसी क्या है, हमारे पास 3 है बिकॉज हमारे पास 3 सच केसेस थे. और ए बी की रो सेट क्या है हमारे पास, वो हमारे पास 4 सच केसेस हैं. सो यहाँ पे अगर आप समझने की कोशिश करें कि हमारे पास जो ए बी के अकर होने की चांसेस क्या हैं या कितनी बार अकर हुआ है, वो हमारे पास 4 टाइम्स है. लेकिन ए बी सी डी 4 पैटर्न्स कंबाइन कितनी बार अकर हुए हैं, 3 टाइम्स. सो दैट मीन्स कि अगर ए बी हमारे पास इस पैटर्न में आउट ऑफ दीज 4 टाइम्स अकर हुआ है, लेकिन सी डी कितनी बार हो रहा है उस ए बी के साथ, वो 3 टाइम है. सो हम कह सकते हैं कि हमारी ओवरऑल प्रोबेबिलिटी क्या है फॉर दिस रूल ए बी इम्प्लाई सी डी, जो कि हमारे पास 75% है. सो आई होप यू हैव अंडरस्टैंड दिस. ओके. Then the interesting thing is, can we find such collocation patterns and the rules automatically and efficiently? So let's see how we can drive efficient algorithm to find them. To find efficient algorithms, we first introduce another concept called participation ratio, PR. So participation ratio, that means the feature F is participating. The participation ratio means that the feature F is participating in this pattern C. What's the probability? Means what is the probability of a feature F participating in a feature C? Okay. So for example, A participating in A, B, C, D. What is the participation ratio for A participating in A, B, C, D? So you probably can see A is a red circle, as you can see here. A is a red circle, red square. So we have 1, 2, 3, 4 and 5 such cases you find A, but we only, every time we find A, we can find A, B, C, D. There are only 2 such cases, like one is here and the second one is here, which is 7 and 14. That's why we get 2 over 5, which is the participation ratio of A in A, B, C, D. Similarly, if you want to find the participation ratio of D in A, B, C, D, so D actually is, you can see, is the blue circle. D is the blue circle. You can see there are only 2 such cases, like one for 11 and the second one for 4. So there are only 2 red circles, or only 2 such cases where we find D, but both of them is completely available or completely participating in A, B, C, D. So that simply says you get 2 over 2, which is 100%, or 1 is the participation ratio for D in A, B, C, D. Then we may drive an interesting property called monotonicity property of participation ratio. That means if suppose we have, where is the cursor? Okay, suppose we have C and C prime as 2 collocation patterns, but C prime is the subset of C. Then for every feature F, if feature is participating in C prime, if a feature participating in C prime, then the probability will be higher than participating in a superset. So this is quite easily can be understood, because you can think about this. If A is participating in AB, if A is participating in AB, sorry, if A is participating in AB, then the chance is higher than A participating into ABCD, as the AB is the subset and ABCD is the superset. So the chances of A participating in AB is higher than the chances of A participating into its superset, which is ABCD, because every time when ABCD occurs, AB will also be there. So that's why when F participating in C, for sure the probability or the participation ratio will be higher than participating in its superset. So based on these monotonicity, and participation ratio properties, we can work out an a priori like algorithm to efficient mining colocation patterns. So let's give you such an example. Suppose minimum feature support is rewritten as sigma and the minimum participation ratio is rewritten as rho. So then we start from a single set feature pattern, start from single set feature pattern. If they are frequent when their support is no less than sigma. So then we can keep using a priori like principle to find their pairs. That means from this single feature pattern we try to find 2 feature patterns, then we try to find 3 feature patterns and grow up to size k using this a priori like principle. Anytime we can stop if the pattern is not frequent anymore, because once it's not frequent, then its super pattern will not be frequent anymore. So this is simply based on the a priori principle. Then based on these participation ratio and monotonicity, we will be able to find all the super patterns of a single feature or the multiple features. So suppose we get a feature which is P and we want to find its super feature or super pattern which is uppercase P, and we know we can get a little bigger super pattern to see whether it's greater than rho. Anytime if it's not greater than rho, its super pattern will not need to be examined because they cannot be bigger than rho anymore. So based on this a priori principle, we can easily work out efficient algorithms to find spatial colocation patterns. So that's the trick, that's the interestingness. Like if we can find the monotonicity pattern, we will be able to work out a priori like efficient processing algorithm. So that's it for today's lecture. If you have any question and queries, you are welcome to write in comments. So thank you.